Hello, class. For our presentation today, I'd like to talk about exercise 11 from chapter 7. We'll go through and look at the problem statement here. So the question asks us to find the general solution to the following ODE. You can see listed below. The first thing we'll have to do is find the homogeneous solutions. So we set the ODE equal to 0. We talked about a method for finding the characteristic polynomial using the following factorial definition. You can see I've replaced each of the terms with the corresponding term in the following polynomial. We factor that out, and here you can see we have lambda minus 1 and lambda minus 1 in parentheses that we can factor out, and what's left over is lambda plus 1. So our two roots are going to be lambda is minus 1 and positive 1. Once we find the roots to our characteristic polynomial, we can find the solutions to the homogeneous ODE. It's just different scalars on x to the power lambda. So for each lambda, we're going to get x to that power, and we can take, any coefficient on those powers to get the homogeneous solutions. So in our case, we have minus 1 and 1, so we get x to the first power, x to the minus 1 power, and we'll be able to take any coefficients on those two terms. Okay, and when we go to find the particular solution, now that we have the homogeneous solution, we can define the Wronskian matrix and do the variation of parameters method as outlined in the chapter. So the very first thing will be to take our homogeneous solutions and create the fundamental matrix. We see the solutions on the top row and then their derivatives on the second row. The determinant minus 2 over x, and then we will look at the modified Wronskian determinants. So the first column will be replaced with our solution divided by the leading term. So we see the solution was 2x squared plus 2, but we divide by x squared, so we get 2 plus 2 over x squared. And then you can see this determinant here, this term of fractions. And then for the second Wronskian determinant, same idea, but the different column, we just put the particular solution in the second column instead. Find the derivative same as before, and we get 2x plus 2 over x. Okay, and so once we found these modified Wronskian determinants, then we can look at the ratios. So we take the ratio of the first modified determinant of the first modified matrix divided by the determinant of the Wronskian matrix. We get these terms here that we'll have to integrate in the variation of parameters technique. Okay, so we look at this function at s and integrate with respect to s. We can choose whatever we want for the lowest bounds, really. This has to do with the fact that we're going to multiply by our homogeneous solution here, and whatever our lower bound comes out to be, it'll just be a constant. And so any constant times the homogeneous solution will also be part of the particular solution. So we can change the lower bounds here to make these look nice. The integration, I'll skip over briefly, but we see we get x squared minus 1 and minus x squared over 3 minus 1. Add these two together, and we see we get 2x squared over 3 minus 2. So this is what we get for our particular solution, and we would like to go ahead and check to make sure that this actually satisfies the original ODE. So we take the second derivative, 4/3 up above. You see we have 2 from the power rule. So we have 4/3 for the second derivative, 4x over 3 for the first derivative, and then here's the function itself here at the end. And we simplify everything out to get 2x plus 2, which is exactly the particular solution we were looking for. Okay, so that's a nice little sanity check to show that we can use the variation of parameters in these Cauchy-Euler type ODEs. And that's really all I have for this presentation. We might talk later in this course about how we could guess and check at some of these solutions to come up with the same idea, but for now we're using the algorithm through the variation of parameters, and we see we get a solution just as fine. Okay, so I'll talk to you guys more about this possibly in class tomorrow. Have a good day. Nice.